All right, how did yesterday go? Good. Did we have an opportunity to work on some homework problems in here from the last few sections? Are there any questions that you want to go over that you may have encountered yesterday that were a little difficult? You weren't too sure on them? Because we can go over those before we kind of finish the notes from this section. Anything from 1.8 or 1.8, 1.9? I think those were the sections. Y equals X.
If it's on the line y equals x, does it have y equals x? Because there's nothing on the other side of the y, so that
Yep.
means it's always on y equals
If you fold it, it would match up, right?
Yeah, I get it.
Yep.
So nothing matches up.
Nothing?
No?
No? We're pretty good so far with symmetry? Awesome. All right, so on page 101, on Wednesday, we completed the chart at the bottom of the page trying to distinguish the difference with these new vocabulary terms. We have even function or odd function. Can we reference that page just for a second? And when I classify something as even, what else do we know about that equation or about that graph? Yeah.
It has y-axis symmetry.
Y-axis symmetry. Okay, so we wrote that down on Wednesday. We also went through the point relationship, and based off the point relationship, we were able to come up with this function notation. So if you take a look at what this function notation is telling us, because we're going to dive a little bit deeper into that today, if we were to plug in a negative x into our equation, okay, for every x that's in there, if we were to plug in a negative x, we should get out, okay, we should equal f of x, which is typically representing the original equation that we start with, like f of x, g of x, h of x, whatever it's called. So what we're testing here is if we plug in negative x, do we get the same equation, bless you, that we start with? Okay, we're going to explore that idea today a little bit further. What about odd? That signifies what type of symmetry? Yes? Origin. O-O. Odd origin. So on Wednesday, we, bless you, 'tis the sneeze season, right? On Wednesday, we wrote the ordered pair relationship, and based off that relationship, we came up with this function notation. So we're going to take a look at this a little bit further. If we were to plug in negative x, we should get out or equal the opposite of the original function that we started with. Can we see how that's written? If we plug this in, this is what we get out. So we're looking for an opposite relationship for this origin symmetry. I think this is kind of helpful. Odd, origin, opposite. O-O-O. Okay, they're all connected. All right, so we're going to explore the function notation relationship a little bit more today. Does everyone have a calculator in front of them? Or someone near them with a calculator? Because we're going to need that today. All right, on the next page, we're going to analytically, meaning by hand, we'll get to the calculator in a second, we're going to by hand prove or show that a function is even, meaning it has that y-axis symmetry. So based off of our notation, we're going to plug in negative x for every single x, and we're interested in seeing if we get the same equation that we started with. Okay, we're going to test it. So let's try the first one. If we were to substitute in negative x, let's see what we would get. 3 times negative x is negative 3x. Negative x squared. Negative x times negative x. That can simplify to a positive x squared. Can we simplify the absolute value a little further? Absolute value of negative 3x. Yeah? It'd just be 3x. Okay, so you can keep the absolute values there if you want to, because a negative inside the absolute value can change to that positive. So we got to ask ourselves, when we plug in negative x and we simplify, do we get the same equation that we started with? Yes. Okay, so we now know that this equation or function is even. If we actually had a graph of it, we would be able to fold it left and right over the y-axis and it would match up on itself. Okay, but no graph is needed because we did it by hand, analytically. So we're trying to see if we plug in negative x, do we get the same function out? Let's try the next one. We're going to plug in negative x for every x. Can we do negative x to the fourth? Can we simplify that? Yeah? X to the fourth. Okay, so the negative essentially just goes away, because if you multiply by a negative times itself 4 times, it ends up being a positive. And then kind of a similar concept is going to happen for the x squared. So after we simplify, do we get the same function out? Yes. So this graph, whatever it looks like, would be even. So you can fold it over the y-axis left and right and it would match up. If you actually wanted to test it on your calculator, you could. But we did it by hand and it's going to share the same result. So those I think were pretty simple. Okay, it's a basic concept. We're going to plug in a value and see if it matches the original. I'm interested in trying a one that's a little bit more difficult or complicated or thought-provoking, whatever phrasing you want to use. We're going to go ahead and try a fraction. Now, before we test it by hand, I want to graph it first, just to kind of lead us in the correct direction. So on your calculator, let's go ahead and hit y equals, and if there's anything in there, you can go ahead and clear it out. And I want to type in that fraction. Now, since it's a fraction, you have to be careful on how you type it in on your calculator. I think it was River last time that showed us that command on your calculator to get top and bottom. Can you refresh my memory on that, River? Because I wasn't too familiar with that.
Alpha y equals.
All right, so alpha and then y equals, and it's the first one, right?
Yep.
Okay, so if you hit the first one, n over d, there'll be numerator over denominator. Thank you. We're going to type in x to the third up top, and then x minus 2x to the fifth on the bottom. Okay. Now here's the thing. If you happen to forget those keys, okay, because you might not be familiar with it, just like I wasn't familiar with it, you can always type in a fraction on your calculator using parentheses. So if you wanted to type it in without using that command, you'd have to put the whole top in parentheses, but then also the whole bottom. You need to tell your calculator you want all of the top divided by all of the bottom. So just in case you can't remember that shortcut to get that particular fraction on there, you can use parentheses. Okay, let's go ahead and hit window. And we're going to use the same window that's on our paper. So -5 to +5, counting by ones in every direction. So with the equation in and the window set, let's go ahead and hit graph. Do we have that picture? Do we need calculator help? All right, so we're going to try to draw a rough sketch of this in our notes, just so we have that visual. Do you guys kind of know, because I know it's a weird looking graph. We haven't really seen these this year just yet, but we will later on this year. Do you kind of know what's happening at what looks like to be +1 and -1, where you get those kind of straight vertical lines in there? Yeah?
Those are like asymptotes.
They're vertical asymptotes. Okay, so on your graph, roughly around 1 and negative 1, because this is a rough sketch, we're going to throw in vertical asymptotes. These are imaginary vertical lines on your graph that it never crosses or touches. So the rest of the graph, it looks like we have a parabola shape in the middle of those asymptotes, so we'll try to draw that in. And then the other left and right sides are underneath the x-axis, so we'll label those too. All right, there's our rough sketch. So based off the graph, can you determine what type of symmetry it has? Can you fold it, rotate it? What's the case? What do you think, Noah? Why is it even? Y-axis symmetry. Okay, so we can classify it as even because it has y-axis symmetry. All right, so we now know the conclusion. We know that this should be an even function, but I'm interested in proving that analytically, okay, by hand. So just in case we did not have the graph to check our work, how can we still get the same result? So this is when we're going to plug in negative x for all the x's and try to simplify it to see what we get. Now, since we already know what the result should be, okay, it should be even. What do you think should happen if we do plug in a negative x into everything? After we simplify it, what should happen? What do you think, Erica? We should get the same equation. Okay, so we already should know what should happen. We want to make sure that we can get there algebraically. So let's plug in negative x. And if we simplify it, we'll have a negative x cubed up top, and then a negative x plus 2x to the 5th on the bottom. Did we get the same equation? No? Yes? Yeah? It doesn't look exactly the same. Are we done simplifying? No. We already said it should match, right? Because it should be even. So there should be some more simplification we can do. How can we get this to look exactly like the beginning one? What do you think, Maggie? Where? On top and the bottom. Okay, well the top already is negative, so that's okay. But on the bottom, I would like to take out a negative. I think that's a good idea. So if we take out a negative, all the bottom terms would switch a sign. So if we have a negative term up top divided by a negative quantity or term on the bottom, those can cancel. And we're left with x to the 3rd over x minus 2x to the 5th. That matches the original, right? Just like we said it should. So the first two that we did at the top were pretty simple, kind of straightforward. But when you start to talk about fractions, that's when things can get a little bit trickier. Because in order to get them to match, at least in this case, we had to do a little strategic factoring. Okay, so just because it doesn't match exactly doesn't mean you can't go further. Okay, maybe you can still manipulate it somehow. Kind of moral of the story there. Does that make sense? Okay, hopefully the visual or graph kind of helped us with that. All right, let's try odd functions. So by hand, analytically, we're going to plug in negative x, and we're going to test to see if we get the opposite of the original function out as our answer. So if everything's exactly the same, it's even. If everything's exactly opposite, it's odd. Okay, those are kind of our two conclusions. So let's test our first one. If we plug in negative x and we simplify it, Is it the opposite of the original? Yeah, everything's opposite, right? Everything's switched to sign. So we'll go ahead and classify this as odd. Everything's opposite. So if we did have a graph, bless you, if you wanted to graph it on your calculator, this shape of graph, you'd be able to flip upside down and it would be exactly the same. Okay, that's our conclusion for odd functions. Let's try the next one. So we're going to plug in negative x. And we'll simplify. So negative 2x for the first term, and then a plus x. We're going to end up with a negative 2x inside the absolute value, but we know the absolute value can kind of cancel out that negative. So it'll change to a positive 2x. Did we get the opposite of our original? Everything switched sign, right? What was positive is now negative, and what was negative is now positive. So this function is odd. If you were to graph it, you could flip it upside down, and it would be exactly the same. Are those pretty straightforward? Yeah.
But if you were to add, instead of having like a 2x plus x times the absolute value, if it was just 2x plus the absolute value, then would it be...
Can you say that again? Like if
okay, so like let's say 2x plus just then, instead of having the x in front of the absolute value, just straight up the absolute value.
So if you plug in negative x, this would be negative 2x plus the absolute value?
Yeah.
So this is not exactly the same as the original, so it's not even.
And it's not directly up.
And it's not odd either. So you're leading us into the next ones. That's a good transition. Okay, so Travis was interested in determining, well, what if it's not exactly the same, and what if everything is not exactly opposite? Okay, what does that lead us into? And that's when we're going to classify it as neither. So if it doesn't match the original exactly, and it's not the opposite of the original exactly, then we don't have either types of those symmetries. It could be diagonal symmetry. Okay, we'd have to investigate that a little further. It could even be x-axis symmetry. Okay, but at least we know it's not even or odd, meaning no y-axis or no origin. So we're basically determining here, is everything exactly the same? Is everything exactly opposite? If it doesn't fit any of those options or conclusions, then it's neither. Okay, it doesn't fit either case. So let's try this one. If we plug in negative x, we're either looking for the same as everything, the opposite of everything, or neither. Let's see if we simplify it. 3x squared minus x. Is it the same as the original? No. Is everything opposite of the original? No. So in this case, we'll write neither. So it does not have y-axis symmetry, and it does not have origin symmetry. We'd have to test the other two types, but at least for now we know it's neither of those options. Let's try the next one. Plug in negative x, and we'll see what we get out. So negative 2x absolute value plus x squared. Is it exactly the same? No. Is it the exact opposite? No. So this would be another case of neither. Pretty straightforward, just like the other ones. Okay, let's try another graphing example. So on our calculator, go to y equals, we'll clear that out. All right, River, I'm going to try this again. It was alpha, y equals, and the first one, just hit enter. Okay, so there's our fraction. We'll type in 2x minus 3x to the third And then we need a 2 absolute value on the bottom. Do you remember where to get absolute values from? Okay, Caitlin? Oh, that's another one. You guys are, yeah, I think you are a little bit more familiar with this calculator than I might be. Okay, so you can go alpha window, the first one. I'm going to delete that for a second. 2x minus 3x to the third. On the bottom, if you hit, this is the way I was familiar with it, if you hit math over to number, it's the first one ABS. Okay, but there's more than one way to bring up these commands on your calculator. Let's go ahead. I think our window is the same, right? -5 to +5. So we'll go ahead and hit graph. Does that look about right? Do we need calculator help? All right, so drawing a rough sketch, it looks like we have kind of half of a parabola on the left-hand side, and then a negative half of a parabola on the other side. Rough sketch. Can we classify it as either even or odd? Can we determine a type of symmetry? Yeah.
It's origin symmetry, so odd.
It'd be odd, okay, because we have origin symmetry. So this would be the one, if you were to flip it upside down, it'd be exactly the same. So now, when we check it by hand, we know what our result should be. If we were to plug in -x everywhere, what should we anticipate? Yeah? For it to be the opposite. Okay, let's check it. So we're going to plug in -x. And it should come out to be the opposite of what we started with. So let's make sure we can get there algebraically. So -2x plus a 3x cubed over 2 absolute value of x. Is that the opposite of what we had? It's the opposite of the top, right? But not the bottom. So, is that still the opposite? Even though it's only one part of it?
It's not fully done.
It's not fully the opposite, so you think both parts have to be fully opposite? Let me ask you this. That's -1/2, right? That's also -1/2, right? That's -1/2, right? Yeah, so when you're working with a fraction, where can the negative go? Just the top, just the bottom, or out front, right? So if we determine that just the top was opposite, isn't that kind of this case? And if the negative is up top, can't I technically pull the negative out front and it would be the same value? So if I were to take the negative that's out of the top, it would switch all the signs. And do we have the opposite of what we started with? Like we said we should, right? Yeah.
What if part of the bottom is opposite, not the entire bottom? Then would that still apply?
Then that would be neither.
Alright.
Yeah. So if you have, like if all of this was opposite, but some of this was opposite, the only way that this would work is if the bottom had to stay the same.
Okay.
Because you can't have like negative and partial negative to still be overall negative. Okay. So it's a little tricky again with the fractions because we have two different places to analyze, the top and the bottom. So fractions can be a little tricky, but remember, if something is the opposite, we have to check, is that the top portion, the bottom portion, because maybe we can pull out that negative and it would still classify it as odd. Do we understand that? Can we see that based off the 1/2 example? Okay. So now that we're kind of getting a little bit familiar with this function notation, like input, output, are we looking for the same thing or the opposite thing? I think this would be a good time for us to try a free response type question. So when we have our free response day next week, because we're getting kind of towards the end of this unit, you might see some similar type questions, okay, practicing this even and odd relationship. So on page 104, we have a table of values for f of x, and you could connect the dots with line segments if you actually were to graph them, and we are, because notice how we have some graphs there. So we're going to use this information to help us with the different questions. So for part A, it says suppose that this function notation is true. Okay, so we know this to be true about this table. We want to sketch a graph of f of x on the interval from -6 to +6. So if this is some information about f of x, let's go ahead and plot it just to see what it would start to look like. If we plot these points and we're going to connect them with lines, looks something like that. So with the information from the table, notice how we only fill in from 0 to 6, but the directions want us to fill in from -6 to +6. So we need to be able to fill in this left-handed side also. How can we do that? They gave us half of the graph. How do we know what the other half should look like? What do you think, Julia?
So f of -x equals f of x is even, so that means it would be y-axis symmetry, so you would be able to reflect it over the y.
We're going to reflect it. Perfect. Okay, so there's that function notation. If you look at it, it's telling us if you were to plug in -x, you would get out the same original equation that you started with. Now, even though we don't have an original equation, we do have original points, okay, based off the table. So Julia said if it's even, we have that y-axis symmetry. So we should be able to take this right-handed side, fold it over, and it would land on the left-handed side somewhere. So you need to visually kind of anticipate if you were to fold it, where those points would land. And that should help us fill in the left-handed side. Does that make sense based off the notation? If it's even, we know it has the y-axis symmetry. So the y-axis and even that we wrote down, I would say that explains our reasoning. Okay, it's an even function, so y-axis symmetry, we can fold those points. All right, let's try B. Sketch a graph of that equation on the interval from -6 to +6. Show or explain how you got the new coordinates for that, which has the same characteristics as the function in part A. All right, so if it has the same characteristics, we're basically taking the same graph. So we're going to use this graph from part A to help us figure out this graph down here. Can we think about what this equation is asking us to do with this graph from part A? If this was our f of x graph? Yeah?
Multiply the y value of the original graph by a -1 and then add 2 to it.
Add 2. Okay, so if those are the operations, how do those translate to the transformations? If you multiply the y value, if we write it out, if we multiply the y value by a negative, and then we're going to move everything up 2, which would affect the y coordinate. Notice how the x value doesn't change. Can we label what those transformations are? You want to keep going, Travis? Yeah.
Reflect it over the x and then just move it up 2.
There you go. X-axis flip and up 2. So we're going to take this graph from part A, and we're going to flip it over the x-axis and then move it up 2 units. Now you can do that individually. You can flip it first and then move it, Or maybe you can use this coordinate rule that we wrote down to help you out. I think the rule might be a little bit faster. For instance, if you take this first point, the x coordinate is not going to change, so it's still going to be at -6, but the y coordinate will change. So if the beginning y coordinate is 5, we need to take the opposite of that and then add 2. So that would be -3. So it's on the same x, but the y position changed. If we keep moving through the points, we can see where the other ones would land. So let's see, -2, 0, -1, 0. I think it'll look something like that. It's still even, right? Still y-axis symmetry, right? So it still has the same characteristics from part A. Check it out. That was a throwback question. Did we do okay? Transformations? Look at you go. All right, last one. Suppose f of -x equals -f of x. Sketch a graph of f of x on the interval from -6 to +6. So again, we can start with those original points from the table. But we got to figure out, what does the left-handed side look like? How do you think we could do that? Go ahead, Hadley.
It's got to be origin symmetry.
Origin symmetry. Okay, so odd function, those classifications, perfect. So if we were to take these points and rotate them 180 degrees, we got to figure out where they would land. Now, this might be a little difficult for us to actually do. Maybe some of you want to flip it upside down and you can see where those points would be. Okay, so we got to think about, if we were to rotate it, where would they land? And I think it's going to look something like this. Another thing you could do is possibly use that ordered pair relationship to help you out. For odd or origin, we had -x, -y. So if you were to apply that rule to the ordered pairs in the tables at the top, you could plot those points and it would work out the same way. Okay, so it's just getting familiar with the notation. What does it signify? What does it mean? What do you know? Where you can go from there. Okay, trying to read and understand math language. We doing okay? Even and odd? Sounds good. All right, we'll end there for today and we'll start the next section on Monday.